Remember, if A is a subset of B, then A intersect B is A, and A union B is B, and we were able to prove that. So A is a subset of B if and only if B complement is a subset of A, and I'm about to show you how to prove that. So just bear these two in mind. So we'll also apply it for the complement. Meaning, for B complement, a subset of A complement, we have A complement intersect B complement as the complement of A union B, which is the same as B complement. We also have A complement union B complement, which is the same as the complement of A intersect B, which is the same as A complement. If you can check this part, is De Morgan's law. So due to this reason, we can be able to prove that A is a subset of B if and only if B complement is a subset of A complement. Or we can also show that if this is the case, then this is the case, because these two are related. So the proof goes this way. Suppose A is a subset of B and let X be an element of B complement. Then X is not in B, and so X is not in A intersect B. So this implies that X is not in A since A intersect B equals to A, because A is a subset of B, and therefore X is in A complement since it's not in A. So we have shown that given a condition that A is a subset of B, if we let X be an element of B complement, it will imply X is an element of A complement. Hence, B complement is a subset of A complement. Conversely, suppose B complement is a subset of A complement, and let X be in A. Then X is not in A complement, and so X is not in A complement intersect B complement. This implies that X is not in B complement since A complement intersect B complement is B complement, because B complement is a subset of A complement. And so X is in B since it's not in B complement. Hence, A is a subset of B, because we're able to show that suppose B complement is a subset of A complement and we let X be in A, X will be in B. So that's it. If I remember, I gave you an exercise to prove that B complement is a subset of A complement will imply A union B equals to B. If you haven't found it yet, go and try it again. So now I gave you a hint. You're going to say, suppose B complement is a subset of A complement, then you first let X be an element of A union B, then you show that X is in B. So which means if this is the case, it means you're going to use that condition here. A complement intersect B complement is B complement. So the same way I have proven, if you can go, you'll get to the same answer. So that's how these are connected. If you try it another way around, you may not be able to connect. So definitions are very much important. Now, a power set of any set, if I may recall, we define it as a set containing all possible subsets of that particular set. It's also known as a partition on a set. So returning to the example before, remember, as set A is denoted by X, an element of universal set, such that X is in A. So suppose a set A is defined by X, an element of natural number, such that X is a composite number at most 8. You know a composite number is any number that can be expressed as a product of two smallest integers. And at most 8, it means less than or equals to 8. So the list of all subsets of A, so since your set A is defined by 4, 6, and 8, because 4, remember, can be written as 2 times 2, and 6 can be written as 2 times 3, and 8 can be written as 4 times 2. So these are the subsets of this set. So they are also known as the partition of a set. So our focus is on the power set of A. We say that X is an element of a power set of A if and only if X is a subset of A. And also for every X in a set A, singleton X is a subset of A if and only if this singleton X is an element of a power set of A. And this is what we need while doing the proofs. So remember, the number of elements in a power set, or the cardinality of a power set, is given by 2 to the power absolute value of A, where absolute value of A is the cardinality of A, representing the number of elements in A. What you have to note now is that under sets proofs, power sets follows set laws. So we'll be just dealing with these proofs. So you can see if A is a subset of B, it biconditionally implies power set of A intersect B is a power set of A, and power set of A union B is power set of B. If A equals to B, it biconditionally implies that the power set of A is the same as the power set of B, and also the power set of A intersect B is the same as the power set of A union B. And all those other laws, when we put the power set, is still applied. Proceeding with our set proofs, this is what I'm going to prove. So I'm proving number 5 now, part A, that A is a subset of B if and only if the power set of A union B is the same as the power set of B. And I'll leave this as an exercise for you to try it out. And also I'll prove if the power set of A intersect B is the same as the power set of A union B, then A is the same as B. So I will leave this also as an exercise. As you can see, this is biconditional, so you have to prove that this implies this and this implies this. So you'll do it the same way and just follow the steps which I'll be using. You won't be lost. You'll get the rest if you really understand what I was talking about. In order to show that A is a subset of B, if and only if power set of A union B is the same as power set of B, we first have to show if A is a subset of B, then power set of A union B is the same as power set of B, and also if the power set of A union B is the same as power set of B, A is a subset of B. So the proof goes this way. Suppose A is a subset of B, and let caps X be an element of a power set of A union B. Now, caps X, an element of power set of A union B, implies that caps X is a subset of A union B by the power set definition. Since A is a subset of B, then A union B is the same as B, and so caps X is also a subset of B. Hence, caps X is in the power set of B. And this proves that the power set of A union B is a subset of the power set of B. Similarly, if cap X is an element of the power set of B, then caps X is a subset of B, and so it will be a subset of A union B, since we know that A union B is the same as B. Hence, caps X is an element of a power set of A union B. And this also implies that the power set of B is a subset of the power set of A union B. Since we're able to show that if caps X is in the power set of B, it will be contained in the power set of A union B. So if the power set of B is a subset of power set of A union B, and already shown that the power set of A union B is a subset of the power set of B, then these two are equal. And our conclusion is the power set of A union B is the same as the power set of B if A is a subset of B, and we just shown that. Conversely, suppose the power set of A union B is the same as the power set of B, and let X be in set A. Then it's in A union B, since we are certain it's in A. And so singleton X is a subset of A union B. This implies that singleton X is an element of a power set of A union B. And since the power set of A union B is the same as the power set of B, then singleton X is also an element of the power set of B. And so singleton X is a subset of B. Consequently, X is an element of B and A is a subset of B. Since we assumed X is in A, then we found out that X is in B. So it follows A subset of B, and this concludes the proof. Proceeding to part B, power set of A union B is the same as the power set of A intersect B if and only if A equals to B. So in order to show that the power set of A union B being the same as the power set of A intersect B will imply A equals to B, we'll assume the power set of A union B is the same as the power set of A intersect B, then we'll let X be in A. We show that X is in B, so we can conclude A is a subset of B. Similarly, we'll let X be in B. We conclude X is in A, so we can show B is a subset of A. That's when we can say A equals to B. Suppose the power set of A union B is the same as the power set of A intersect B, and let X be in A. Then X is in A union B. And the singleton X is in the power set of A union B. Since this singleton X is a subset of A union B, it follows that singleton X is also an element of power set of A intersect B. Since the power set of A union B is the same as the power set of A intersect B. And also, singleton X is a subset of A intersect B. Consequently, X is in A intersect B, meaning X is in A and X is in B. Hence, X is an element of B and A is a subset of B. Similarly, if X is an element of B, then X is an element of A and B is a subset of A. So the word similarly means you are going to do it as you similarly let A, you found B. So the only difference is now you are starting with X, an element of B, then it will go to X, an element of A union B, since X is in B. And also, it will lead you to singleton X being a subset of A union B, which implies that singleton X is an element of the power set of A union B. And since you know that the power set of A union B is the same as the power set of A intersect B, you'll conclude that singleton X is also an element of the power set of A intersect B, which will lead you to singleton X being a subset of A intersect B. Consequently, you'll get X an element of A intersect B. So X is in A and X is in B. So here you'll have hence X is in A and you'll conclude B is a subset of A. So it's just a similar process, just swiping A and B. Hence A equals to B if the power set of A intersect B is the same as the power set of A union B. Conversely, suppose A equals to B and let caps X be an element of the power set of A union B. We'll have to show that caps X is also in the power set of A intersect B. So we can say the power set of A union B is a subset of power set of A intersect B. Similarly, we'll let caps X be an element of power set of A intersect B. We'll have to show that it will be in the power set of A union B, so that we can also conclude that the power set of A intersect B is a subset of the power set of A union B, so we can say the two power sets are equal. Now, caps X an element of the power set of A union B will imply that caps X is a subset of A union B. And since set A equals to set B, then A intersect B is the same as A union B. Hence, caps X is also a subset of A intersect B. And it will be the element of the power set of A intersect B. And this indeed proves that the power set of A union B is a subset of the power set of A intersect B. Since we assumed caps X is an element of a power set of A union B, we have shown that cap X is an element of a power set of A intersect B. And similarly, we let caps X be an element of a power set of A intersect B. Then caps X is a subset of A intersect B, which is the same as A union B, since A equals to B. Indeed, caps X is also a subset of A union B if it is a subset of A intersect B, and therefore it is also an element of the power set of A union B, which then also proves that the power set of A intersect B is also a subset of the power set of A union B. Finally, the power set of A intersect B is the same as the power set of A union B if A equals to B. Since we're able to show that the power set of A union B is a subset of the power set of A intersect B, and also the power set of A intersect B is a subset of the power set of A union B. So you see, understanding matters. And this brings us to the end of this video. So please don't forget to try your exercise and see how far you understand.